Hello everyone. In the week 3 we are going to discuss about divide and conquer strategy. It is a strategy which we generally use to solve different types of problems. In this week we will discuss about merge sort, that how to use merge sort by using the divide and conquer strategy. So in today's we are going to cover about what is the divide and conquer strategy, how merge sort works, pseudocode of merge sort, and then C++ code implementation, the time complexity of merge sort, some examples and advantages and disadvantages of this. So let's start with divide and conquer. So it is basically a technique to solve a problem that breaks the problem into smaller sub problems, right? And we solve them recursively and combine their solutions at the end. So it basically involves three steps. One is the divide, conquer, and combine. So divide is break the problem into smaller problems, into smaller sub-problems. Then conquer is solve the sub-problems recursively. And then combine the solutions of sub-problems, which is called as the combine. So divide and conquer involves the three key steps, three major steps: divide, conquer, and combine. Divide, dividing the problem into subproblems. Conquer, solve each subproblems recursively. And then combine the third step is combine all the solutions to get the overall solution of the problem. So if we represent it mathematically, the equation is denoted by Tn equals to Dn plus A times T of n over B plus Cn, where Dn is the time to divide the equation. That is the dividing the problem into subproblems. Then A times T of n over B is the time to solve subproblems. Now you can see here this is a recursive part because the equation is Tn and it is Tn over B because we are going to solve each subproblem recursively. And Cn is the time to combine the solutions. So this is the overall mathematical equation representation of divide and conquer. Dn equals to dn plus a times Tn over b plus c of n. We use divide and conquer in a number of problems like merge sort, which is a sorting algorithm. It divides the array into halves, then again and again until the problem size becomes 1. Then it sort them recursively and then later on we combine the solution, merge the solution. Quicksort is a sorting algorithm, but it works around a pivot element. We need to select the pivot element and then we partition our array according to the pivot element. It is again a recursive approach. Binary search is used for searching an element into a list of elements. The binary search works on the sorted list of elements, and in binary search we reduce the search space in half every time we search the element. Then one is the Strasson's algorithm, one of the very important algorithm for matrix multiplication. It reduces the multiplication operations. Then closest pair, it is a problem which is used to find the computational geometry. So we use it for the divide plane, find closest pair, and so on. So if we talk about the merge sort, then merge sort is basically a comparison based sorting algorithm in which we compares the elements, um, because there are some non-comparison based algorithm also in which we do not compare the elements to sort them, but in case of merge sort it is a comparison based algorithm like bubble sort, selection sort, insertion sort, in which we compare the elements to sort them. It is a stable sort. That means it maintains the relative order of equal elements. Then it is not a in-place sorting algorithm. Unlike bubble sort, selection sort, insertion sort, which we covered in the last week, all of those are in-place sorting algorithms, but merge sort is not an in-place sorting algorithm. That means it requires an additional memory to perform the sorting operation. The worst case time complexity of merge sort is big O of n log n, which is very less in comparison to big O of n squared for bubble sort, selection sort, insertion sort. So basically in this one, in merge sort, we divide our array into two halves every time, recursively sort each half, and then we merge the sorted halves. So we got a sorted array. So if we see the step-by-step process, the algorithm, how does it work basically? And okay, before the algorithm, yeah, let's move on to this part actually, that how merge sort works. Let's see, initially our array is 7, 3, 2, 16, 24, 4, 11, 9. This is our array. Then in first step, we will divide our array into two halves. So first half will consist of 4 elements since initially there are 8 elements. So it will consist of 4 elements in the first half, and second half will also have the 4 elements. So 7, 3, 2, 16, 2, 4, 11, 9. Then again we are going to repeat the same process recursively. So again we will divide the array in two halves again. So 7, 3, 2, 16, 24, 4 and 11, 9. Then again we are going to divide it. We are going to split it again into halves. Make sure we perform the splitting operation into halves till each sublist consists of one element, right? So 7, 3, 2, 16, 24, 4, 9 and 4. So all sublists are of one element now. Now we we start to perform the sorting algorithm and merging them. So we take a pair of elements and we start sorting them. So 7 and 3. If we sort this, it becomes 3, 7 and we merge it. Then 216 becomes 216. 24, 4 becomes 424. 9, 11 becomes 9, 11. Then again we take one pair. We merge them and sort them, right? We merge and sort them. So after merging and sorting them, it becomes 2, 3, 7, 16, and this becomes 4, 9, 11, 24. Again, we merge and sort them. The process is recursive again. The process is recursive again until we get one single list of sorted elements. We repeat the process. So again, we merge and sort them. So it becomes 2, 3, 4, 7, 9, 11, 16, 24. So this is the idea behind the merge sort. The first step is splitting the array till each sublist consists of one element. And then the second step is merge and sort each of the sublist until you get the one full list. So if I go to the algorithms process again, the base case, if the array has 0 or 1 element, that means it is already sorted. So we do not need to perform any sorting operation and we can stop it. Then divide, find middle point. That is, we find the, since we are talking about the arrays, so we take the middle element in terms of index. Then recursively sort left and right half. Again, the left half will be from left to midpoint and the right half will be from mid plus 1 to the right, where left is the index of leftmost array, array of the leftmost element, and right is the index of the rightmost element in the array. And then the next step is combine the merged two sorted halves into one single sorted array, right? So this is the pseudocode. So the pseudocode involves two steps. One is the merge sort and one is the merge operation. It involves two operations, merge sort and merge. So we perform the operation till the left index is less than the right. We need to find out the middle element till the left index is less than the right. As soon as there is only one element left, that is left is equal to right, we stop the process, right? So mid equals to floor value of left plus right divided by 2. We are taking the index of middle element. Then we recursively call the same process. We recursively call the same process. A is the array from the left to the mid, that is for the left partition, and merge sort again recursive for the right partition, that is from mid plus 1 to the right. And once all the recursive partitions are done, then we call the merge operation on the left, mid, and right. So we merge them, right? Now, the merging operation, how does merge operation works? We give the parameters are array, left index, middle index, and right index. So we take two variables here, n1 and n2. N1 is the mid minus left plus 1 and right is the n2 is the right minus mid. Create two arrays L and R, left and right. Okay. So what we do in the merge process basically, we take two arrays. We create two arrays L1 and L2. L and R. N1 is the number of elements in the left subarray. N2 is the number of elements in the right subarray. So we create two arrays L1 and L and R. The size is N1 plus 1 and N2 plus 1, right? So the number of elements, we are creating two arrays, left and right. Look, we are having an array, like for example, we are having, okay, 1, 2, 3, 4, 5, 6. Let's say, for example, this one. So my left portion consists of elements 1, 2, 3. My right portion consists of elements 4, 5, 6. We will create two arrays, left and right. Since it is not an in-place sorting algorithm, it requires additional memory. So we need to create two additional arrays, left and right. So the array L consists of the elements of left subarray and R will consist of all the elements of right subarray. So first of all, in the left array, you are going to copy all the elements from the left partition. Then the second loop, in the array R, you are going to copy all the elements from the right partition, right? We are going to terminate the arrays by infinity. That means this denotes the end of the array. Now, we need to start merging the process. So how do we merge it? Suppose we are having two sorted arrays, like I am having 2, 4, 6 and one other array is 1, 3, 5. Let's say we are having these two arrays. This is left, this is right. Make sure all of these with both of these arrays should be sorted because we are sorting and merging them. So individually these two arrays will be sorted. Now we compare the first element of both arrays. We compare the first element of both arrays 2 and 1. Now 1 is less than 2, so 1 will be copied in the array A. 1 will be copied in the array A. Now we compare 2 and 3. 2 is smaller, so 2 will be copied. Then compare 3 and 4. You will increment the pointer to the array of which you are copying the element in array A. This is your array A. So again, you start with 1 and 2, the first element of both arrays. Since 1 is smaller than 2, so 1 will be copied to the array and we increment the pointer of the array R. So it reaches to the element 3. Then we compare 2 and 3. Now 2 is smaller, so 2 will be copied. Since from array L, we are copying the element, so we will increment the pointer of array L. Now pointer is on 4 and 3. So 3 and 4 will be compared. Now 3 is smaller, so 3 will be copied and pointer of array R will be incremented. So pointer will reach to 5. So now the pointer is on 4 and 5. Now 4 and 5 will be compared. 4 is smaller, so 4 will be copied. Now, since 4 is copied into the array from array L, so pointer of array L will be incremented and it will reach to the element 6. Now pointer is on element 5 and 6. So 5 and 6 will be compared. 5 is smaller, so 5 will be copied. Now, since the array R is ended, so there is no place to increment the pointer. So the remaining elements is only 6, so that will be copied. So your sorted array becomes 1, 2, 3, 4, 5, 6 after merging these two arrays, right? So we use this loop. We use this loop to merge them. We compare the corresponding elements of left and right. I is the index, I is the pointer towards the array L, and J is the pointer towards the array R. If element of array L is smaller, it will be copied to array K and pointer of array L is incremented. Otherwise, the element from array R is copied to array K, array A, and pointer of array R, that is J, is incremented. So this is basically the merge step. So what you are going to do in the merge process, you are creating first of all two arrays, left and right, L and R. In the array L, you are copying the elements of the left portion, and in the array R, you are copying the element of right portion, and then we are merging them, right? So this is basically the merge process. Okay. In case of its implementation, you are supposed to implement it, right? Just implement it in C++ by using the same algorithm. Again, you need to create an array A, which will hold some of the elements, declare an array with some elements, and then call these two functions. Call just merge sort, and because merge sort is calling the merge function. So you just need to call the merge sort function in the main function, and it will perform the sorting. And the same code you have to write over there. Now, to calculate the complexity of merge sort, one of the easiest way of calculating is the Master's theorem. So let me give you a brief introduction about the Master's theorem, that how does it work. Basically, Master's theorem is a shortcut to solve the recurrence relation, as our this merge sort is a recurrence relation. So we use it for to solve such type of equations. Master's theorems works only for the equation which are of this form: Tn equals to a times t of n over b plus fn, where fn is any of the function in terms of n. It may be n, it may be log n, it may be n square, it may be any of the function fn. So to solve it, we need to evaluate for master theorem. To solve the master theorem using the master theorem, we need to evaluate n raised to the power log a base b. We need to evaluate n raised to the power log a base b. And once you evaluate n raised to the power log a base b, where the value of a is found from here and the value of b is found from here. Once you evaluate n raised to the power log a base b, we compare it with this given function fn. We compare it with fn. Now, there can be three cases. Either fn equals to n raised to the power log a base b minus epsilon, where epsilon is some constant greater than 0. Then your solution is going to be this: theta of n raised to the power log a base b. You do not need to do anything else. If fn equals to theta of n log a base b, then your solution is going to be this, case 2. And if fn equals to omega of n log a base b plus epsilon, then your solution is going to be theta of fn. This is the simplest solution actually. So how to use it? Again, first of all, you need to identify that your equation is of the form Tn equals to Atn over b plus fn, where A denotes the number of subproblems. Like in merge sort, we always divide our equation into two parts. We dividing it into two halves. B is the factor by which the subproblems are smaller. Like again, it's by 2 in merge sort, because we're dividing the array into halves. And Fn is the cost of work done outside of the recursive calls. So we need to calculate log A base B. We compare n raised to the power log a base b and fn. And we compare the functions, and then based on these three cases, is it equal to this and this, like based on the previous solutions, this one minus epsilon equal to or plus epsilon, where epsilon is some positive constant. Our solution depends on this one, this or this. Our solution may be either theta of n raised to the power log a base b, or theta of n raised to the power log a base b log n, or theta of fn. Let's see one example for binary search. Let's say for binary search, our equation is Tn equals to a raised to the power Tn over 2 plus theta of 1. Now, if you compare this equation with this equation, the value of a is 1, b equals to 2, and fn equals to theta of 1, which is a constant. Now, we calculate log a base b. So, log 1 base 2, which is equal to 0. Now, we need to compare n raised to the power log a base b, which comes out to be n raised to the power 0, which is equal to 1, with fn, which is again theta of 1. So these two are same. As you see, these two are the same. That means the case 2 is applicable here. So the solution becomes theta of n log a base b log n. If you put on the values, it becomes n raised to the power log n raised to the power 0 log n. So it becomes theta of log n. So this is the complexity of binary search. If I give you one more example, so let's say Tn equals to 2Tn over 2 plus theta n. So if we solve it here, the value of a equals to 2, this one, b value of b is 2, and fn equals to theta of n. So n raised to the power log a base b, if we calculate, it becomes n raised to the power log 2 base 2, which comes out to log 2 base 2 is 1. So it becomes n raised to the power 1, which is equal to n. So if you see here, this n, if you compare fn, that is, this is your fn. If we compare fn with n raised to the power log a base b, this part, they both are same, because this is also n and this is also a function of n. So again, your case 2 is applicable over here. So which comes out to be theta of n raised to the power log a base b. So your solution becomes theta of n log n. So if we talk, this is about the merge sort, that the complexity of merge sort. Every time we are dividing the array into two parts, splitting into two parts, and the array size is reduced by 2 every time. So in case of best case, the complexity is n log n, in case of average case, and in case of worst case. In all of the cases, the complexity is big O of n log n, and the space complexity is big O of n. That is the number of elements in the array, because when we are performing the merge operation, we need to declare an array of the same size. So the space complexity is big O of n for this. Again, if we take a step-by-step example of this one, let's say my array is this one. So first step, this is the level 0. At the first step, we are having the complete array. In the second step, we will divide the array into two halves. So the first half will consist of 4 elements and the second half will consist of 3 elements. Then again we will split it. So the second level, so 38, 27 will be one sublist, 43, 3, 9, 82 and 10. Then again we will split it, because again we need to split until each sublist consists of 1 elements. Then we start the merging and sorting process. So first of all, we will merge these, right? So 38 and 27 becomes 27, 38. 43 and 3 becomes 343. Then if you merge these two, it will become 27, 38, 343. It becomes 3, 27, 38, 43. If we merge 9 and 82, it becomes 9 and 82. Then if we merge these two, it becomes 9, 10, 82. And then if all these two are merged, we get the complete array. So this is the final array, final resultant and sorted array. If we talk about its space complexity analysis, so recursive call stack, since it's a recursive algorithm, recursively a stack will be managed over here. So the recursive call stack big O of log n, because the depth of the recursion tree, and each recursive call uses the constant space. We are using the temporary arrays big O of n. So merge operation, because the merge operation requires the temporary storage to store the left subpart and right subpart into the arrays. So this is the maximum extra space needed for doing the merge. So big O of n is the maximum space total complexity. If we are using the linked list, so this extra space can be used, can go up to the big O of 1, right? But for arrays, we need to use the big O of n additional space. So advantages and disadvantages. Merge sort is best because it guaranteed you big O of n log n time complexity in all the cases. It is a stable sort because it maintains relative order of equal elements. It is well suited for large data set, and as well as it is best for external sorting. External sorting is the sorting when your data is too large that it cannot fit into the computer's memory in computer's RAM. So we store the data on the external storage device like your SSD and all. So from there, from the external storage, you are reading the data in memory and then you are sorting it in some data segments. So it is very good for that purpose, external sorting. And predictable performance, as we said, that in all the cases, the time complexity is big O of n log n. The disadvantages are big O of n additional space requirement because it requires an additional space. It is slower than quicksort for small arrays due to the recursion overhead. Again, since it's not an in-place sorting algorithm because it requires additional memory space, and recursive implementation may cause a stack overflow for very large arrays. So these are the few of the disadvantages, but still merge sort is one of the very prominent sorting algorithm due to the time complexity. Because if we compare the merge sort with other sorting algorithms, you will see the merge sort big of n log n as like quicksort, but the worst case of quicksort is n squared, whereas merge sort is still have n log n. But quicksort requires less space log n, whereas merge sort requires big O of n. That stable, it is a stable sorting algorithm, but quicksort is not a stable algorithm. Heap sort is also a big O of n log n. It is again a very good algorithm and its space complexity is also big O of 1, but it is not stable. And bubble sort, as we have seen already, that big O of n squared. Insertion sort we have already seen, these are big O of n squared. So if we see the real world examples, as we said that it is used for external sorting. External sorting whenever data does not fit in the RAM. And we also use, so whenever data is so large that it cannot fit in the RAM, computer's memory, it is all on the hard drive or the SSD. So from there you need to read the data in segments into the memory and then perform the sorting. So in that case, it is the best suited. It is very well for the databases also. Inversion count is always a we need to count the inversions actually in an array, right? So like inversions when the elements are not in correct order, and used in recommending systems. Merge sort is used in recommendation system, like you see that when you see the some movies, so it recommends you movie that these you may like, or when you go to a shopping website, your website recommends you that these products you should purchase based on your history and your choices. So it is used in recommendation system also. Linked list sorting, merge sort is optimal for linked list. As we said, in the case of linked list, it just requires big of one extra space. It is used for it is used in parallel processing because in merge sort we can perform the segmentation in separate parts and we sort the individual parts parallelly. And it is whenever we need to maintain the relative order of equal matters, so it is possible in merge sort. There are some variations of merge sort as well, like bottom up merge sort, natural merge sort, tim sort. Tim sort is basically a combination of merge sort and insertion sort. It is used in Python and Java, which is it is used in built-in functions of the sort built-in functions of Python and Java. We use their merge sort and insertion sort. Multi-way merge sort because We can merge more than two subarrays at once in doing by using the parallel algorithms and optimization techniques. So switch to insertion sort for small subarrays, avoid copy operations by alternating arrays, and pre-allocate temporary arrays. So these are some of the techniques which we can use for the optimization here. So key takeaways for this session is that divide and conquer is a fundamental algorithm for design paradigms. Merge sort is a classic example with big O of n log n complexity. It is stable but requires an additional space of big O of n. It is well suited for large data sets and for the external sorting. It is foundation for more complex algorithms. When we should use the merge sort, whenever stable sorting is required and whenever we are sorting the linked list, whenever the worst case performance matters, and for the external sorting scenarios. So this was all about the week 3, the merge sort. See you in the next week. Till then, bye.